Good day to one and all, and you're all very welcome to today's webinar. My name is Martin O'Gara. I'm a developer with Civil and Structural Computer Services, and today's webinar we'll be talking about our MasterFrame finite element analysis. We do hope to go into quite a bit of detail today, taking you through the various aspects of the finite element analysis, and this will be more of a training style session rather than a fast-paced demonstration. So hopefully you'll pick up quite a bit of detail here today. Some of the key features of our MasterFrame finite element analysis, for those of you who aren't familiar with it whatsoever, is it's an analysis add-on program to MasterFrame to allow you to easily, in MasterFrame, model structural engineering components such as slabs and walls and ramps. So it is using finite shell elements. For those of you who maybe aren't familiar with what a shell element it is, we use a quadrilateral finite shell element basically, which is a very good general purpose element for modeling planar surfaces such as slabs and walls and ramps, etc. So you can actually put together 3D assemblages of these surfaces in MasterFrame to model many different types of shapes, as we'll see as we continue. So it is an add-on program to MasterFrame. It isn't separate. So if you've got MasterFrame, you can purchase the MasterFrame FE add-on and have the ability to do all these things alongside and in through your MasterFrame model. So you could have a steel framed MasterFrame model with using our finite element add-on to model the shear cores, for example. Or obviously you could have a concrete frame building using the finite element to model the slabs and such. So it is very versatile in terms of the applications of this program. What we have here in the finite element analysis program is largely an analytical tool to allow you to analyze these aspects. As we go on through, you'll see that there are some notions of being able to extract perhaps areas of reinforcement from slabs, but it is primarily an analytical tool, an add-on to MasterFrame. Other key features are that we are using a very fast and state-of-the-art solver for finite element analysis, which certainly resolves the bottleneck of waiting for hours in an analysis to complete. In addition to that, and this is perhaps one of the most important things for you guys as engineers, is what you do with these finite element analysis results post-analysis. Setting up the model is the easy part, as is applying your loads. As we'll see, all of that can be done very, very quickly and easily, especially if you're familiar with MasterFrame. But then once we get our analysis, obviously we need to be able to do something with those results to produce some design information. And we have a wealth of very powerful tools for interpreting your finite element results, as we'll see. So I thought you might like to see some examples of what you've got up to with our MasterFrame finite element analysis over the years. So this perhaps might be a typical example of a flat slab construction. We've got some parapet walls modeled in as a structural walls in and through the finite element analysis. So you can see an assemblage of walls and columns and beams and systems of ground beams here, all included in the one model. Here we actually have a steel component. This is some type of steel component of welded plates, which someone has used the finite element analysis to model up. So it isn't exclusively restricted for building purposes. As long as you understand what the scope of the program is and what its analytical limitations are, then you should feel comfortable for using these finite elements for other applications other than building structures. Another flat slab structure with a mixture of timber, steel and concrete and slabs and walls all in the one model. Quite a complex structure here of a really intricate system of shear walls with openings modeled using the finite elements, laterally supporting a composite cellular type structure. And actually down at the bottom of this structure we have a finite element floor slab modeled at the base as well, which may indeed be a pile supported raft or something like that. More complex arrangements of shear walls, so not just standard rectilinear shapes by any means. You can put together an assemblage of any plane surfaces you wish to achieve some really interesting shapes. And perhaps this is the more typical, what you might expect to see, your typical flat slab with shear walls and concrete columns. This would be one of the primary applications that we would see people using our finite element analysis for. Again, another smaller structure with which may be a more of a domestic type of house modeling with slabs and walls all modeled as part of one structural model. And that's just something we're going to come to in a moment or two. So we're going to get on with this here, and we're going to get straight into setting up our finite element model. Now, this is the type of model that I'm going to take you through the production of today, and we're going to go through it in the various stages of making one story and then producing another story, and we may even look at the end of introducing a raft foundation. It's a fairly simple structure. We've got a limited amount of time, and I do want to do this from scratch to show you the maximum amount of coverage and training that we can provide in this space of an hour. There are many ways in which you can produce your initial geometry. So we've gone into MasterFrame here, and you can produce your initial geometry for modeling the finite element surface. In many ways, you can import something from Revit. You can import something from DXF. Those obviously would get you up and running much more quickly. But here and today, we want to start off by modeling and creating this geometry of this structure that I've just shown you from scratch, and I'm going to use my standard snap grid tools. Now, for those of you who maybe are long-standing MasterSeries customers, you'll know that the 2013 version of MasterSeries introduced some really new and interesting snap grid or AutoCAD style, or I shouldn't say AutoCAD, but CAD style drawing facilities in the MasterSeries. So we're going to use those today, and I'm simply just going to start snapping and drawing, and what I'm going to do is going to create a wall or a side of the structure which is 20 meters long. So I can actually just start typing 20 here, and that will override the current dimension and direction. And I'm just going to turn on my DirectX graphics, and my line produces itself a little thicker there. And again, I want to produce another angular line coming out like this, so I can see the angle and I can see my dimension. However, I can just say something that's 10 meters at 45 degrees gives me something like this. Now, having done that, I can then continue to model this basically using things like my perpendicular tracking line from my existing member that I'm coming from. And in fact, I can turn my snap grid off, which maybe helps me in that I'm not snapping on items that are at intermediate grids, and I can only snap at tracking points. So I've just turned the grid off easily by clicking down below. And I want to create another side of the structure which is 10 meters long. So again, just typing in the dimension in the direction that I'm currently going in. And let's create another line which comes from here. And I'm just going to extend this down a little bit and leave that at that for the time being. And then for this side, I'm going to create that going up, and I'm going to say that that's at a distance of 12.5 meters. And I'll just take this all the way along and orthogonally snap in here. Now I can get rid of that member just simply by over-clicking it again as a quick, if you like, cheats way of deleting that member. Again, I want to split this. I'm actually going to model two finite element surfaces on this because I do want to model a construction joint halfway through it, so that I don't have moment transfer between one part of the slab to the other. So we're going to do that, and I'm going to introduce that join at a distance of, we can say it's 12.5 meters from that end, snapping in and going up and orthogonally snapping up here like so. I'm going to introduce a little opening, and for that I do need to turn on my snap grid again to be able to freely click inside this area, and I'm just going to snap in some openings at some dimensions like this. And again, I'm just using the snap grid in this situation. I'm not actually using my text input. So just to quickly snap in a slightly irregular shaped opening in this slab. So all I'm doing is drawing lines, and these lines are the same way you would draw lines as in standard MasterFrame members, but we're going to use these lines to model the boundaries, or to say that they are the boundaries of the finite element surfaces. So we'll see all that as we continue. Now I'd like to drop in some columns to this. This is the main outline of my slab and my opening. So I'm going to create some columns. Again, I'll take the snap grid off. And again, I can do, there's lots of ways I can create columns. In fact, we have up here a specific add column facility, but I'm going to continue using my snap grid. So again, in 3D, I'm picking up the vertical tracking line. So I know now if I type in a distance of 3.5, it'll snap me precisely at that location. And coming along here, let's come along to a distance of, if I actually just type in 5 meters, it snaps me at 5. Let's move down, enter 3.5 to get me another column in that location. And let's just go for a midpoint snap at that location. Again, going down 3.5, and we'll keep going in that type of fashion. And again, a midpoint snap here. And in fact, I can use my tracking there to, instead of to avoid me typing, just by hovering over a point, I create a temporary tracking point, and that gives me the ability to basically snap at an orthogonal tracking line along with that. So I'm going to go here midway, and my tracking line there doesn't work in the orthogonal direction, so I'll just type in the dimension of 3.5, and we don't have too many columns on this structure. Now I'm not going to put a column at the end here, because I do want to show you that we can deal with irregular column layouts and geometries. It doesn't have to be prescribed that you have columns at all locations or anything like that. So and I'll just have one or two more columns to put in, just continuing to go at this rate. And an interesting thing I can do here to introduce some intermediate columns is if I hover my mouse over these 2 points to create temporary tracking points, because that's a temporary tracking point, I get tracking lines at all the members which are aligned with or perpendicular to that member. So I'm going to go with a line perpendicular to the member here, and as I approach this tracking point, just to reintroduce that, it also has a perpendicular line to one of the members it's associated with, so I get a point of intersection automatically occurring there, again allowing me to put that column in precisely where I want it to be. Now let's just keep that a little bigger, and so we can all see what we're doing. And again, just hovering my mouse over this point and this point will give me a tracking point where I want it to be in this location, moving vertically down by my column heights. That's actually all the columns on that side. Just a few more columns on this side. We'll put one at the midpoint, one at the corner, and we'll just use our tracking point there to pick up that location. And finally, I think I'll just have a mid column up here, so there isn't any regularity so much to our columns at all. Oh, I accidentally was moving in the wrong direction there, so I'll just do a quick undo. And this is where it's useful to have your view in such a way so that you aren't ambiguous in terms of the direction you're moving. And let's go 3.5, and going out this direction, have a temporary tracking point there to create a little system of members that I can use to frame out to do my wall. So just hovering there again to allow me to create a system of 2 walls here at either side of my 2 openings. And essentially that is my main geometry complete, using my CAD style drawing techniques in MasterSeries. There are many more powerful features such as polar snapping. You can access all these snap settings by coming into these areas, but we won't go into those in any great detail today. Those were introduced in some detail in the MasterSeries 2013 launch webinar. There was a MasterFrame webinar shortly after that, which goes into those in quite a bit of detail. So now we're ready to start to introduce some finite element surfaces. Excuse me. Finite element surfaces in this geometry we've created. So we're going to go up to our finite element editor menu, and here we have FE surfaces. So quite simply, we've got a default FE surface here to start off with, and the basic premise is that you create the main border of a finite element surface. So quite simply, I can start clicking around the border here to pick up these members. However, I can make use of something called the auto select feature, which means if I window a group of members, it's just going to pick up the main border members basically. So those are the main border members selected. I know that it's successful in creating a surface because it's colored it in, and I want to create an opening in that surface as well. So over along here, again, this auto pick opening is selected, which means if I pick inside this area, it'll detect that I'm picking these members. But if I don't check that, I can just simply manually select the members going around the perimeter. But they're doing it with the auto pick to pick them up all up automatically, all the 6 members of the perimeter of that opening. And again, I can see that coming through here. Let's have a look at here what a finite element surface looks like. So we've got a finite element surface. All the attributes and properties of the finite element surface are defined in this one area, whether it be the material, the loading, the openings, any edge support or release conditions are all specified in this one area. So let's look at what we can create. One of the most important things about a finite element surface is its local surface axes. So when we look at this surface, we can see that it's drawn a little template picture of it here, which is not very exciting for this simple shaped surface. But this shows us that the X direction and the Y direction is in the plane of the surface. Another helpful tool to help us to see the local surface axes is to draw the local result axes, local coordinate axis system. So for this surface, the red is always the X, the perpendicular in the plane is the Y, and the out of plane is always the Z. So this is the way our result axis goes for this one. That will dictate many things. It will dictate our finite element results when we go to look at results and we talk about moments in the X and Y directions. This is the axis which controls that. That can actually be adjusted here. You can say that I want to rotate that by 45 degrees. You would really not want to do that in this case. Or you can align it with 2 nodes, which is maybe something that we could do for this edge. So those are some important things to look at there. There is also the opportunity to swap the local z-axis so that it goes the other way, but we're happy with the z-axis pointing upwards in this instance. So just to note that there is a difference between what we call our global MasterSeries axes, where we've got X, Y, Z, and our local finite element surface axes. They are 2 distinct axis systems. Moving on through our different tabs, one of the other things we want to do is obviously define a material. We have some basic materials here in a little library which you can add to by clicking the Save button on your current material. So we can just simply say I've got a C30 concrete, apply that, and that basically just fills in these basic properties here. And this is our default slab thickness here, which we'll leave. There are other types of material. You can have an orthotropic material, i.e. material that has different properties in 2 principal directions, 1 and 2, which is the X and Y axis essentially, which can be separated from the X and Y axis by an angle. So this is the angle between the one axis and your X axis. And we can have a layered material. And interestingly, we also have a ribbed material which was introduced throughout partway through the year in 2013. So this might be something that many of you didn't pick up on. And what that actually allows you to do is model more of like a composite style flooring system where you've got a ribbed material. And primarily where this is used is for people going in to the dynamic analysis to model response factors for finite element floor slabs. where you've got a composite floor slab. You want to model the deck as a rib, and then model your attached beams for actually going into the dynamic analysis and establishing response factors. So that's primarily what that gets used for. So we'll stick with the isotropic material here. Now, we also want to define some what we call attached beams, and we might feel that maybe these spans are a little bit too long for the slab itself to support, maybe with some edge condition loading that we might apply. So we're going to say that these are attached beams. Now you might say, well, I've already drawn all my members, and you might even have gone into MasterFrame and defined a property on those members, or into the MasterFrame line element properties. But all the members that are part of a finite element surface will be treated as dummy members until you say that they are an attached beam. So looking at the section properties here now, it tells us that. It says all of these members are dummy finite element members, even the ones internally. So only when you say that they are part of the attached beam group of this member, these two, now they will contribute structurally to this. Now how they contribute structurally can be changed, and again this was a feature which was introduced partway through 2013, and really what we want to do here is to say that these are connected to the bottom. They're bottom justified to this floor slab, and you can create an additional Z direction offset, but no, this will automatically look at the size of the member and the thickness of the slab and offset them from each other. You won't see that happening with the line element as such, but it will happen at analysis time. So just useful to go in and see what the property is on these members. It's come through as a steel section, which must have been the default section I had whenever I was drawing the members initially, but obviously we don't want that. We want a concrete member. And what I am modeling here, because I'm modeling the additional part of the attached beam, I just want to model the downstand, because the main T section of this slab, or of this downstand beam, is actually modeled by the finite element shell. So we don't want to use a T section, we want to use a rectilinear type section, and I'm going to say that that's 350. So say for example the overall depth is 550, so 200 of slab and 350 of attached beam for that. And now if I look at that with my full 3D on, we can see actually that it has modeled it with the beam justified to the bottom of the slab. So that offset will be accounted for in the stiffness calculations of the member. A little bit more on the other consequences of doing that whenever we do our analysis and come to that end of the business. Okay, well, let's pick up the pace a bit. Back into our finite element surfaces. And other things that I want to define on this finite element surface are some edged releases. And we do that through the edge support condition. And quite simply, all I have to do is say that I want to model releases, and I want to say that they're released in all the rotational axis directions. It's generally the simplest thing to do is to say it's released in all the rotational axes, regardless of the axis of the line that you're dealing with. So I'm going to say actually these two lines are released, so you won't get a moment connection between the beam and the column. And again, on this axis, I won't get a moment connection between the slab, this slab, and the other slab that I've yet to model. And actually, I've just noticed that I've missed a few columns in here, which I'm going to need to pop in. Otherwise, I'm going to be suffering quite badly on some bending moments across there. We'll come back to that. So that's our edge release condition. You can actually have different release conditions, but by simply going to, let's say, a second release condition and specifying that. But no, we're specifying everything in release condition 1. It is actually important that we decide which surface we specify the release on, because it will have different behavior. Okay, as I was saying, the edge release condition is relevant. It is actually important as to which side you release it on. It's like putting the end release on the end of a member. There's a difference between putting the end release on the end of a member and the end release on the end of the column. It's the same type of philosophy. So we're going to go forward here and look at defining some loading on this surface. So let's get some loading on. So we can simply say add new, and we've got different types of loading: full surface, point, line, patch, and perimeter type loading. Let's do a full surface load, and we'll say that it's a live load in the y direction of -3.5. I should say in the materials, the density is already modeled, the thickness is already here, so the density of the dead load self-weight density load will already be taken into account. So back to the loading, that's my full surface area loading. Other types of loading are things like perimeter loading, so we can add another load. This is my second load, say that it's a perimeter load. Again, keep it at live, maybe give it a value of -10, and it goes around the full perimeter. Now what you can actually do is break that perimeter load up by telling it to stop and start at certain nodes. We can display the node numbers here, so I want it to start at node 13 and go to 4, so in a clockwise fashion generally is the pattern it follows. So rather than going 4 to 13, we'll go 13 to 4 using this little picker and OK to that, and it follows its way around like so. Now other types of loads are loads that we can place not just on the full surface on the perimeter but anywhere inside the surface. So we add new, and those are indeed points. Point loads, line loads, or patch loads can be located anywhere within the surface. Let's just turn the nodes off, and we'll make it a line load. And again, live is fine. Let's give it a value of -15. And the location mechanism we use for this load is something called load point coordinates. And these are additional two-dimensional coordinates in the axes of the local surface axes of the surface, which we can create. Now we can create those very, very quickly for the entire surface at all the existing node points by using this button and using this LP button to label them. So these aren't node points, these are load point coordinates which have been created inside the surface at all the node points. So we've got load point coordinate 1. Note it's only a 2D coordinate system for this planar surface, so this is 0, 0, etc. I can very, very easily just delete all those. We can use this tool here to quickly just add load point coordinates at specific nodes is another way of doing it. So just check that off. Let's clear all that and just go back to where we were. But equally I can go in and just start typing in load point coordinates. So I can type in a load point coordinate, an x coordinate of 2 and a y coordinate of 3, and I can actually see those load point coordinates as well. I can say display the local surface load point coordinates. We do have a load point coordinate editing tool, so you can actually go in and say edit the load points, and let's take load points 14 and 13 and say shift them in the y direction by say -2 meters, and we can see them moving by that amount. So that's a quick way of shifting and moving load point coordinates around without actually going into the list and manually editing their coordinates. Okay, so we can say that we've got a line load located at some of these points. So I can say here, using my picker again, I can say that I've got a load point, or a line load, which is located to load points 15 all the way to 13 and across to 12, and OK to that. And now I get my line load appearing. Interestingly, not many people know this, but you can also put in a second value here to linearly vary that load from its start point to its end point, if you need to do that. Other types of loads, add new, and we're going to do a patch load here. This is our fourth load. Again, it's a live load. We'll just say -1. Take the load point coordinates. Let's reset them, and we'll go from 8 to 9 to 6 to 7, and OK to that. Now I'm going to introduce you to another nice little feature, again, which is maybe underutilized or maybe people don't know about, is the varying load option. And that's whereby we can have this patch load, not just one value, but a varying surface of load. Now, how simply we do that is by specifying 3 values of loads located at the 3 load point coordinates. And the 3 values, along with the 3 points, gives us a plane about which we can calculate all the other values. So quite simply, if I were to say for load points 6, 7, and 8, so I'll just type that in for expediency, 6, 7, 8 are my 3 varying load points. So I'll say I've got -1 at 6, and 0 at 7, and -5 at 8. And that gives me my varying load. I can see it drawn graphically there. So I can see the -1, the 0, and then over at 8 it will be -5, and probably actually a little bit greater at node 9. So it will actually be, it'll calculate the values here. Right, so we can continue from here, and we've got to create our second finite element surface here now. So we're going to, at 27 minutes to go, we've got a lot of work to do, so let's go and do that. It may be a good idea for me, once I've created this surface, in fact I'll create a few walls here and then I'll pick up another structure which I've moved on a few stages, just to avoid me repeating stuff and wasting time. So what we do want to create some of the walls here, so I'm going to go back to main border. I've still got one surface, so I can simply say add another surface. And this time I'm going to use my auto select main borders. Instead of windowing, I can actually just pick. I do have to be in the add remove mode inside that to quickly create that wall. And all I'm going to do there is in the materials specify that it's got an increased thickness of 250. And the other important point here is the edge support condition, not release but restraint. I'm going to say that it is fully fixed on the base of this wall on this member. And likewise I can add a third surface, main border, auto pick inside here. It's using the same material as the last one. The edge support condition again is fully fixed on this line. So I've now got primarily some finite element surfaces of beams and walls, and we need to continue to define my finite element surface on the other side. What I'm going to do now is quickly go forward a little bit and open up another file which has the second surface created. It's created in exactly the same way, so we don't need to continue to talk about that. And so I have here the two surfaces created together. Now with all the loads that we've generated, this side will have some loading on it as well. It's useful to see how those loads are coming across. We can use here our standard MasterFrame frame load diagram to look at that, and for all the different load cases. Now you noticed when we were generating those loads, just like any other MasterFrame load, they had a load group, they had a direction, and they had a value, and they followed the same rules for the normal MasterFrame loads. So they're combined in loading cases in exactly the same way as normal MasterFrame member loads. So we can see here our loading cases. We've only got 2 of them, and the factored loads are then presented in this colored coordinated key here. So we can see we've got a factored live load of -6, but obviously if I go to all cases and just look at live load only, we can see here, yeah, this is -4, and these are now our unfactored loads that we're looking at, because we're not looking at a particular factored load case. So that's a good way of validating those loads, that they're all there. And indeed I can see my density. Well, my density load's not actually coming in, so let's take care of that. So we'll go to loads and density for self-weight, and we need to turn on density, and it's D1. And let's look at that frame load diagram again. Oh, sorry, that's the frame statistics, not frame load. And we may have something missed there in this little example, but it seems that, oh yeah, we've got our density button, D button, not pressed on over here, so that didn't include the density. So now we've got our density values coming in, and we can validate what our slab self-weights are and such as well. Okay, so a good idea at this stage is I want to actually make this into a multi-story structure, but I also want to make sure that it's not full of little problems before I do that, and it's a good idea to analyze the structure before we do that. I should point out a few other things that I may have done in this that weren't done in the previous steps. Is I went around and defined concrete columns on all my columns, and also put on some support reactions. Those are about the only extra things that have been done apart from the second finite element surface. Now, as I say, a good idea to analyze this at this stage, just to see that we don't have any problems. So we're looking at what our meshing is. Our default mesh is a 1 meter square mesh. So let's just come out of here. It meshes, and let's analyze. And we're analyzing okay without any issues. I always like to check my deflected shape just to make sure that we haven't missed a support. And then we can see the effect of the edge release coming through there as well. You can see you're not getting continuity of the slab where you've got your edge release. Same thing as well for your connection to your walls. You're not getting bending coming through from the wall, slab to the wall and such. So that's really all I want to validate and verify at this point. And before I go back in and choose to duplicate. So the duplication process to make that from a single story into a multi-story is quite the same as you would do for any normal MasterFrame. So we simply can say duplicate nodes and members. By default, it's selected all the nodes in the structure, which is what we want actually in this case. I want to move up by 3.5 meters in the y direction, and number of repeats 1. No tie members because I'm actually duplicating the columns as well. Otherwise, you might get additional members going, let's say, from this node to the node at the next level, and that's duplicated itself upwards without any difficulties. Now, it will have duplicated up the finite element surfaces and everything as well. One thing that we should do after a duplication like this is to go into our geometry, model cleanup, and pack and delete unused nodes. And just to be sure, we'll do the same for the members. Now, I always like to look at my support conditions, and I can see, probably due to the packing, that the support condition isn't there, but it's also a good idea to go in and have a look at our finite element surfaces. And now we've gone from the 4 surfaces to 8 surfaces. But for these surfaces here, we'd want to ensure that the edge support condition didn't copy up, which it has. So we need to clear that out essentially from these 2 surfaces. Using the clear button clears the selected members from the condition you're looking at. So that's a quick way of sorting that out. Now, again, we'll probably need to move on a little bit and choose my next phase of this file. If I were to analyze this quickly here now, saying it needs to be remeshed, which is fine. And let's go into our output, and let's start taking a first look at our analysis output. So as I said before, we'd like to look at deflections, but now we're going to move on from this and look at our actual finite element, shell element results. So we're getting some bending moments here. Now, before I start looking at results and particular values of results, it's always a good idea to check your maximum percentage error. Now you might say, if you're maybe not that familiar with finite element analysis, well, why would there be an error? That is the nature of finite element analysis. If we perhaps don't have a refined enough mesh, a small enough mesh to capture the variability of the stresses which may be occurring, then the resulting analysis could be erroneous by a certain percentage. So it is expected that you would look at this here, and using your color contour diagram you can see the extent of the overall percentage error is 20%, and we can see that error is increasing typically around the column heads, which is to be expected because that is indeed where our areas of stress concentration are. So going with a default global mesh size of 1 meter isn't going to be adequate for the detailed design and picking up of the detailed forces around column heads. We do need a more refined mesh in those regions. So to introduce that, we go into our editor, and in the finite element meshing option, we have our first, aside from global meshing options, which simply allows us to specify the global size, There are some other options to mesh to members inside finite element surfaces, which really isn't something generally you would do. But we want to go into the local mesh intensities, which allows us to specify at node points a smaller mesh size than the global size. So I'm going to say a mesh size of something like 0.15 at a radius of influence of 3. So it's going to reduce the mesh size at my selected nodes. Now I can pretty much select all the node points. I got to be in a select mode, of course, and maybe excluding some of the points which don't that aren't points of stress concentration, or where I have a supporting column. And we'll see the effect of that, and we'll come out of here, exit the editor. It's saying yes to remesh, and I can then analyze again, and have a look at my results. And this time, well, my overall percentage has come down by about 7%. And this is typical in that even with a refined mesh, what actually happens is the percentage error increases close to what we call the point of singularity. But the error drops off quite rapidly. In fact, we can look at that in a 3D sense, and the error drops off quite rapidly from that point of singularity. Now, I suppose just to go into a little bit more detail, the way we're modeling the column wall interaction here is, yes, the column is modeled with its stiffness and its axial stiffness and bending stiffness, but its interaction between the slab and the column is still a distinct pin head point. So to that point, to that extent, with an infinitely small area of support, we get infinitely high shears and bending moments. So the true answer here in terms of bending values and shear values is that they basically approach an infinite value. And that is what's known in finite element analysis as a point of singularity. But of course, we're not interested in what's happening at a distinct point. We're more interested in what's happening around the face of the column, for example. And this is where I'm happy to accept the error that I'm getting here, because I know it does drop off quite rapidly to a more acceptable value. Otherwise, you'd be going back and reducing your mesh size somewhat further to reduce that error further still. But back in my actual results, if I were to go and look at, let's say, my moments in the x direction, and again look at it in 3D, it's a good idea for me to then look at it not just for the whole area, but just for a distinct set or a distinct finite element surface. And this is where introducing you to our finite element display options. You can get to it using the viewing tab down below, or right mouse click and say show viewing options. And we've got finite element display options, and here you've got lovely handy facilities for filtering to certain FE surfaces. So I can filter to FE surface 1, for example, or do a multi-select and filter to FE surfaces 1 and 2, which is quite useful for me here at this stage. Now back here I can see from my 3D presentation of the contour again, at the points of singularity my bending moments do reach quite peak values. And indeed they would be quite high values. But as I said, you certainly wouldn't want to be designing for those values. And in fact, the values are at such peaks that they're sucking up all the color range as well. Now, we're not interested in those, but we are interested in what goes on around the column face. And the very handy utility we have for filtering out those points of singularity is something called peak smoothing. And peak smoothing simply has a look at whether or not we have a column at a point of singularity, gets the column size, and basically uses the size of that column to basically filter out results within a certain region and smooth those values out. You can define a peak smoothing diameter if you wish to override the default column sizes, but it's better to use obviously the default column sizes, because you may have variable column sizes. So we can see the effect that has and the tremendous effect it has on the extents of the bending moment values. Now, going forward and looking at how we can interpret these results, we have our various different results of Fx, Fy, which are in-plane membrane. So this is our in-plane axial force in the slab. We might be more interested in, say, looking at Fy values on our shear walls, for instance. But let's focus on the slab. And then we've got our bending values of mx, my. Now these values are the bending, mx is the bending moment which creates stress in the x direction effectively, not about the x-axis but in the x-axis. We can change the number of contours, but for design purposes we're more interested in our wood armor moments. So these are our mrx and mry, so we can look at those values of moments also. It is actually interesting to look at, as well as the legend, we have the facility to show values at characteristic points, which gives us the max and mins, the peaks and the trough values annotated, so we can quickly see what values are as opposed to interpreting them from a color. But from those wood armor moments, obviously you can establish your areas of reinforcement, and this is where we've actually given you a little bit of design help here by taking the wood armor moment and looking at areas of reinforcement. So we can look at the AS required in the bottom XX, for example, and let's choose to work to the Eurocode with 500H grades of steel, FY or concrete grade of 30, and those covers are fine. And doing so gives us the contour diagram of the bottom reinforcement, excluding the top values, obviously. Now, it would be a good idea, if you're obviously looking at multiple cases, to go down here and look at the envelope of ultimate cases. But in this case, we've only got one case, so that's not going to make any difference. Now, with that, it can be useful to, say, drop that down to a minimum number of contours and introduce, using this handy little utility, some additional user-defined contours. Now, you can introduce user-defined contours not just for areas of reinforcement, but for any of those quantities. But when it's an area of reinforcement, we give you this handy little utility of saying, right, well, I'm ranging between obviously 0 and 2625 somewhere. So we can say I want color bands at values of, if I go tens of 200s, and we'll stick at a 200 spacing, and let's just give me lots of values at different size bars at 200 spacing. You can basically fill that in whatever way you want. And if I apply the setting to that now my color banding is split up in accordance with these values of that I've picked up here. Now there does seem to be a high value here somewhere, which is if you like sucking up the color, and you can see actually those colors appearing. Good little tip there is to switch on the 3D and put it in a profile view, and you'll see these little spikes occurring in these locations. And again, those are occurring due to points of singularity around corners and things like that. So it might actually be quite useful to say, if I were to put that back in a flat view, let's annotate the surfaces, and realistically my maximum values of areas of reinforcement there is maybe 600 odd, so I can actually cap that. I can say the maximum value is 800 for instance, just giving myself a little bit of leeway, obviously. And now you can see it actually, anything above 800 is this grey value, so there obviously there was another higher value at that location up there, so you might take that to 1000. And that just, these max min values help you to utilize your color a little better, so that points of singularity with erroneous peak high values that aren't smoothed out by the peak smoothing end up, you can filter those out as well using max and min values in these locations. So that actually can be generated into a DXF output. When I switch across the contour lines, I can do a DXF output into AutoCAD, which a detailer can then use to, with these color banded values, to then start detailing reinforcement, and that will be quite useful. However, it's quite a different story whenever you go for the top area of reinforcement. The bottom area of reinforcement is fine generally to look at with contours, because in a slab situation, your bottom values generally don't tend to have extreme peaks and variabilities. But for top values, you certainly do get, because of your hogging over pinhead columns and such, you do get peak values occurring over column heads, which give you very high values of reinforcement, but obviously then drop away quite rapidly. So it's often not useful to look at areas of reinforcement for the top in the contour area. So for that, actually, you find your section diagram is your friend basically in this scenario. So we can quickly go and say, right, I've got a section diagram which goes from this point to this point, and you can apply the setting on that, and sorry, not that, that's area of reinforcement. I'm just going to change its direction so it's drawn pointing up and not down, and let's just change the scale a little bit as well, and we can annotate that, show values. Now this gives me really nothing more than what the contour is, but it just extracts the results out from the contour. But really where this section diagram is absolutely useful for top reinforcement is the facility to do some strip averaging. So if I were to average that over a design strip width of 2 meters, you can see that that 4,000 figure drops away very rapidly because of the fact that that value is reducing very, very quickly away from this point. Now on this edge, actually, this is a 2 meter wide and only 1 meter of the strip is inside the slab. So the averaging is only done over the actual part of the strip that is in the that actually encounters or intersects with the material and not with the fresh air. So we can continue putting section diagrams on in that nature. So I can add another section diagram, say from say this point across to this point, and continue to do strip averaging and set them up. Now again, because we're running out of time, I'm going to switch forward to another model which has a more comprehensive arrangement of section diagrams set up. Really adding more section diagrams is just a more of a repetitive process, and I've got hopefully another model here which, going into output, and into section diagrams, gives me, and let's just go to planet level 1, a system of section diagrams which are set up in one particular direction with strip averaging. Now I've chosen here to show them all with their values. Now you can also say that we want to see the values or see the distances to the points of contraflexure, and because things are jumping up and down a little bit, some areas you get more than one value. So that can be quite useful as well to for detailing purposes, to know where, you know, basically those bars need to start and stop. In addition to that, all of these section diagrams here, all 6 of them, are all in one section diagram set. Now I can add another set. In fact, I have another set here for all the section diagrams, and I've got 4 of them now in this direction for the S required top YY. So it's useful to group your section diagrams into different sets so you can quickly flick between them and have them displayed independently from each other, so you don't have to have all the section diagrams displayed at once. Now, so I could add another section diagram set, say for shear, where I might want to extract out some values for punching shear purposes. Let's draw my nodes, and for punching shear I might want to include a rectangular section diagram. Simply add a point with 2 dimensions, say a length and a width in meters, and I'll just flick that around to the other direction again, apply that setting, reduce the scale, and that actually picks up for me. Oh, I'm actually still looking at AS required top YY. The fact that I've called it shear down below doesn't obviously know that it's shear, so I need to look at the FV max, which is my maximum vector summed X and Y direction shear force values. With their values gives me some shear at a perimeter around this area. Now obviously you might decide as an engineer, well, I don't actually need to go into that level of detail, I'll just take the axial force in the column to do my punching shear. But where you've got variability in your spans or openings, then obviously the shear force value can vary around the perimeter quite considerably, and this can be quite useful for detailed situations such as that. Okay, a few other things we'll hopefully squeeze in before we close up on this webinar, and one of which is the modeling of a raft foundation. So I have another file here which has that included, and quite simply all that I've done is actually duplicated a level down to get lots of members around the perimeter, and created a third level of a finite element surface at the base. So I've got all the surfaces that I had before, but this time my ninth surface is a slab surface. What I've done also is removed the point support conditions from the bases of the columns. However, if you do have point support conditions, you can use those as well. And the key thing obviously which makes this a raft is the fact that it has a spring area support. So if I look at my edge support condition, the only thing I have to do for this surface is say what its soil modulus value is. Basically its volume modulus of kilonewtons per meter cubed value. So essentially this reads that it's going to take 10,000 kilonewtons per meter squared to create a 1 meter displacement in my soil. And the other important aspect as well is that I'm saying that it's compression only. So if there is any situations where, perhaps unlikely in this scenario, but if there are any situations where I've got uplift due to lateral loading or overturning, then that's going to be able to be modeled in a non-linear fashion simply by checking this box. So let's have a look at the analysis results on that. So the modeling of rafts is very simple and straightforward. So we look here at our deflected shape again, and this time we can see that we're getting movement at the base of the structure. It isn't hitting any points of hard support at any of these locations. It is settling, the ground is compressing, or the spring is compressing. So I can actually look at that spring area support, and again with the viewing, it's useful for me to go into my viewing options, filter FE surfaces to FE surface 9, and here I have with my contour or my legend what my actual spring support value is, my kilonewton per meter squared. That obviously is giving you your ground bearing pressure essentially over underneath the base of that raft. And otherwise the design of the raft for the areas of reinforcement is exactly as per you would do for a normal flat slab arrangement. You're still going to use your values of contouring of reinforcement and your section diagrams for that type of thing. I'm just looking back through my list here to see if there are any other items which are outstanding, and the one area which we haven't covered yet is the ability to model patterned loading in your finite element analysis. And thankfully I have another little model here which has everything set up on it, and I'll take you through the processes there. Now you will notice that if I go into the editing here, let's look at just planet level 1. I think I've got the pattern loading set up for this level but not for the roof. Previously I didn't have all these internal members, and now I've introduced them. I've simply drawn those in the way I would draw in any other member. They are a normal member, but the fact that they're in a finite element surface means they're automatically determined and detected as dummy members. So we don't need to worry about specifying that. What these members give me the ability to do is to split the slab up into different alternate regions. Now, the first thing that I want to show you is that for the finite element surface in the loading, I would need actually to say that my load is not L1 but L alternate. Because how we achieve pattern loading is by allowing the load to be associated with different groups in different regions. So I don't want all my load to be always just L1. I want it to have the ability to split itself up into different load groups. And I would do the same thing for any other load essentially on this slab. So now the one other area where you need to make alternate is the density. Good idea again to look at your frame load diagram, and this shows you that you've got mostly, well, I didn't do this side, but essentially my density actually is still D1 in these regions. Now that's again controlled in the density for self weight, and over here I would set this actually to D alternate. So that's the one other area where I do need to set that. Now what does D alternate and L alternate actually mean? Well, if I go to my FE editor, I have alternate load areas. Now let's turn off the frame load diagram so that it's not stealing all the colors. And I have this set up here essentially. I've got load set 1, load set 2. And what this load set is actually, and if you read it there, it's actually the same number as in your load group number, i.e. D1, D2, L1, L2. So this essentially means that all the load in this area, whether if it's DA, it'll be D1. If it's LA, it'll be L1. Likewise, this will be D2, L2, etc. But in the finite element analysis, what we're trying to achieve by pattern loading is the maximum, if you like, sagging moment in certain parts of the slab. So we need to pattern the load not in a checkerboard fashion, but in strips. And in strips not just in one direction, but two directions. So in addition to load sets 1 and 2, I've also patterned the load in load sets 3, 4, and 5. Because in this area, my number of columns in terms of the patterns changes. So I have to be a little inventive here of how I actually manage that. So I'm actually using 3 load sets. I'm using load sets 3, 4, and 5 in this area. So those are my 2 key pieces of information. My third key piece of information for setting this up is how I define my load combinations. First of all, here I've got all spans loaded. So load sets 1 and 2, not 3, 4, and 5. So that basically means everything is loaded with the same amount. Now I've got load sets 1 is factored, 2 is unfactored dead only. So that's going to give me patterns in these directions. So I'm going to get max, min, etc. And 3 and 4. Now I'm still only using 1 and 2, but look what happens when I switch across here. Now I'm using the patterning in the other direction, where I've got max, min just in these 3, and then back to max again. And because I've got 3 sets, I've got a lot more combinations of patterns to consider. But I'm covering all my bases there of how I will generate patterned loading in those areas. And at analysis time, for the load case, for example, where I have load sets 3, 4, and 5 included, it will know that the loads in this area that are DA are now D3. It will attribute the load to the correct load group for the load case it's dealing with. And your analysis, you will see that reflected in your deflections and in your results. And that's essentially how patterned loading is handled. I want to just go back to my PowerPoint presentation and finish off just by maybe giving you a little bit of a preview of what is coming in the 2014 version. Our 2014 version, I mentioned earlier about the pinhead modeling you get between slabs and columns and the issues that creates and how we overcome that by peak smoothing. However, a superior approach to that is actually modeling a stiff region in the slabs where you've got interaction between columns and walls, and the 2014 version is going to have that built into it. It's called a slab support stiff region modeling. So all you really have to do is to say, right, well, I actually want to have stiff regions modeled, and you select your columns where you want that to occur at, or by default say you want it to happen for all support locations, and it automatically will model stiff regions and take care of the meshing and everything that needs to be taken care of. And also then when you go and look at your results, it will help you in terms of filtering out results from these areas and just focusing on the results that are in the slab and not in the stiff zone. So that's going to be quite a useful thing. The other thing that's coming in the 2014 version is the ability to look at stresses and not just forces. So we have the ability to look at your direct stresses, your shear stresses for different faces of your shell elements, but also various different yield surface criteria. So whether it's von Mises or Drucker pressure for brittle type materials, lots of different types of stress outputs going to be given there as well. Just remains for me to say, ladies and gentlemen, thank you very much for your time here today, and we look forward to seeing you at our next webinar.